Ever wondered what the difference is between scalar and vector quantities? Today, we are diving deep into this topic. In the universe of mathematics and physics, quantities are usually classified into two broad categories, scalar and vector. Let's start with scalar quantities. These are the simple ones. They are defined by their magnitude alone. Think of magnitude as the size or the amount of something. It doesn't matter where you are or in which direction you're looking. Scalars are the same from every perspective. Some examples of scalar quantities include temperature, mass, speed, and time. So when you say it's 30 degrees outside or that a car is moving at 50 miles per hour, you're talking about scalar quantities. You're talking about how much, but not in which direction. Now here's where things get a little more interesting. Vector quantities are like the sophisticated cousins of scalars. They've got a bit more to them. They're not just described by their magnitude, but also their direction. To fully understand a vector, you need to know both how much and which way. Take displacement, for example. If you say you walked 3 miles, that's a scalar, but if you say you walked 3 miles north, that's a vector. You've included direction. Other examples of vector quantities include velocity, force, and acceleration. To represent vectors visually, we often use arrows. The length of the arrow symbolizes the magnitude, and the direction of the arrow, well, that represents the direction. So vectors give us a more complete picture of certain physical quantities. So in simple terms, scalar quantities have only size, while vector quantities have both size and direction. This might seem like a small distinction, but as we'll see in the upcoming scenes, it has profound implications for how we understand and calculate physical phenomena. Stay tuned as we delve deeper into the fascinating world of vectors. Now that we understand what scalars and vectors are, let's move on to how we can add and subtract vectors. Imagine vectors as arrows flying through space. Each arrow has a certain length, which we call magnitude, and each points in a specific direction. When we talk about adding vectors, we're essentially combining these arrows in a way that accounts for both their lengths and the directions they're pointing in. There are two common methods for vector addition: the head-to-tail method and the parallelogram rule. With the head-to-tail method, we place the tail of one vector at the head of the other. This creates a new arrow or resultant vector from the starting point of the first vector to the end of the second vector. It's like following directions from a map. First you go a certain distance in one direction, then you turn and go in another direction. The resultant vector is the most direct route from your starting point to your final location. The parallelogram rule, on the other hand, creates a parallelogram with the two vectors serving as sides. The resultant vector is drawn from the starting point of the vectors to the opposite corner of the parallelogram. It's the diagonal that slices through the parallelogram, representing the combined effect of the two vectors. Now, what about subtraction? Subtracting vectors is a bit like adding, but with a twist. We reverse the direction of the vector that's being subtracted, then we add it to the first vector. Picture it this way: if you're trying to subtract the effect of a wind blowing east from your westward journey, you'd essentially add the effect of a wind blowing west. Remember, when dealing with vectors, we must always consider both magnitude and direction. It's not just about how far you're going, but also where you're headed. By mastering vector addition and subtraction, you'll find yourself better equipped to navigate the world of physics and beyond. You may be wondering, how do we deal with vectors that aren't simply up, down, left, or right? That's where vector resolution comes in. Picture this: you're in a game of pool. The cue ball hits the 8 ball and it shoots off at an angle. In this situation, the movement of the 8 ball is a vector. It has both a magnitude or speed and a direction. However, this vector isn't simply up, down, left, or right. It's at an angle. So how do we make sense of this? This is where the concept of vector resolution comes into play. Vector resolution is a technique that allows us to break down a vector into its horizontal and vertical components. To continue with our pool analogy, imagine drawing a right triangle where the hypotenuse is the path of the 8 ball. The other two sides of the triangle represent the horizontal and vertical components of the vector. To find these components, we use trigonometry, specifically the sine and cosine functions. The cosine of the angle gives us the horizontal component and the sine gives us the vertical component. These components can be thought of as the magnitudes of the vector acting in each respective direction. So, when we talk about the components of a vector, we are referring to the individual parts of a vector that result from its resolution. For example, if a vector has horizontal and vertical components, these parts indicate the magnitudes of the vector acting in each respective direction. In the case of our pool game, the horizontal component could represent how much the 8-ball moves horizontally across the table, while the vertical component could represent how much it moves vertically. By understanding vector resolution, we can break down complex vectors into simpler parts. This helps us analyze and understand situations where vectors aren't just moving in a straight line up, down, left, or right, but are instead moving at an angle. So, vector resolution allows us to understand the individual parts of a vector in various directions. You may be thinking, why does this matter? Why do we need to know the difference between scalar and vector quantities? Well, the answer lies in the world around us. From the simplest of motions to the most complex of phenomena, scalar and vector quantities are at the heart of our understanding of the physical world. Take, for instance, a game of soccer. When a player kicks the ball, it's not enough to know how hard they've kicked it. We also need to know the direction in which the ball is kicked. Here, the force of the kick is a vector quantity, having both magnitude, the strength of the kick, and direction, where the ball is headed. Or consider a car on a road trip. The speedometer might tell you the car's speed, a scalar quantity, but without knowing the direction of the car's movement, a vector quantity, you won't have a complete picture of the car's motion. In the realm of physics, understanding vector quantities allows us to explore concepts like force, motion, and electromagnetic fields. We can calculate the net force acting on an object by adding various force vectors, or determine the resultant velocity of a moving body subjected to various velocities in different directions. In computer graphics, vectors are used to represent the position, velocity, and acceleration of objects, enabling us to create realistic animations and simulations. In the field of engineering, understanding vectors is essential for designing structures and mechanisms, as it allows us to analyze forces, movements, and stresses that occur in different directions. In meteorology, wind speed and direction, both vector quantities, are vital for weather prediction and understanding climate patterns. These examples illustrate that understanding scalar and vector quantities is not just about knowing the numbers. It's about comprehending the full picture, the magnitude, and the direction. It opens up a world of analysis, prediction, and problem-solving across numerous fields. Understanding the difference between scalar and vector quantities is akin to recognizing the difference between just knowing a number, scalar, and comprehending both the numerical value and the direction, vector. So, let's sum up what we've learned today. We've delved into the fascinating world of scalars and vectors. Scalars, we discovered, are quantities that have only magnitude. These are the numbers that tell us how much, but not which way. Examples of scalar quantities are temperature, mass, speed, and time. They're all about the size or amount, and they don't involve any direction. On the other hand, we have vectors. These are the quantities that possess both magnitude and direction. They tell us how much and also which way. Examples of vectors are displacement, velocity, force, and acceleration. We can visualize vectors using arrows, where the length represents the magnitude and the direction of the arrow shows the direction of the vector. We then looked at the addition and subtraction of vectors. We learned that when adding vectors, we need to consider both magnitude and direction. The head-to-tail method, or the parallelogram rule, can be used to add vectors. And when subtracting vectors, we reverse the direction of the vector being subtracted and then perform vector addition. Both these operations take into account the magnitudes and directions of the vectors. We also explored the resolution of vectors and their components. Vector resolution involves breaking down a vector into its horizontal and vertical components, applying trigonometry, specifically the sine and cosine functions. The individual parts resulting from this resolution are known as the vector's components. And finally, we underscored the importance of understanding these concepts. The distinction between scalar and vector quantities is akin to knowing a number versus comprehending both the numerical value and the direction. These are fundamental operations that allow us to manipulate and comprehend various physical quantities in both magnitude and direction, opening doors to problem-solving and practical applications in various fields. With a solid understanding of scalars and vectors, you're now better equipped to tackle problems in physics and beyond. Stay curious and keep exploring.